Hello, my name is Ian Walker. I'm an applications engineer at GMW, and today I'm going to review some Coreless clamp-on current probes that have been developed by GMW. So these probes have no magnetic core, unlike most conventional DC and AC current sensors. And the fact that they have no core gives some potential advantages. And so we'll cover that in this review. The original development for these sensors started in an electrochemical application where the requirement was to measure DC currents on bus bars in anode-cathode configuration. Up to about 50 pairs in one electrochemical tank. The current rating was about 4,000 amps. And the problem was that the background magnetic field from the array of currents was significantly higher than the magnetic field from a single current. And this turned out to make the use of a magnetic core clamp impossible. So what we're going to discuss is some of the current probes that developed from that technology. So this is a discussion on clip-on and clamp-on current probes, and particularly how they might be used for in-vehicle or test stand monitoring. So start with a general overview of where the measurements might be made. This is, say, typical of a vehicle, particularly a car. So it shows either onboard charging, a battery and a motor drive, or an external charger. Now, typically, the currents are deliberately very close together. The aim is to make the distances as short as possible so that the vehicle can be compact, as light as possible. And so those considerations make it quite difficult to find a place to insert a current measurement. And it certainly emphasizes that current devices have to be clip-on or clamp-on, and they also have to be small. If it's going to be an in-vehicle test, they also have to be light, and they have to be resistant to vibration and also resistant to temperature extremes. So the sort of typical clamp-on meter that's used for handheld applications generally is not suitable. They're too big and they're generally not tolerant of high temperatures or moisture. So something smaller and able to sustain difficult environments is necessary. So the first one is what we call a clip-on current probe. It has a 27 millimeter aperture. So the sort of thing is something like this. So the aperture here is 27 millimeters. You can see that it's very small compared to the aperture, both in the in-plane version, but also perpendicular to the current. It's very slim, so you don't need very much axial length to insert the probe. And this shows a clip used on a bus bar in a charger, and it is just clipped around and the leads. It's an analog output, so that goes to some sort of analog processing system. So just a quick review of the specifications. The output on this one is analog, 0 ± 2 volts. The current ranges 250 amps to 2000 amps. Frequency range DC 75 kilohertz. The error and sensitivity about 1%. One important thing is the output signal change in a magnetic field is quite low, 0.2% for a 40 millitesla field. And 40 millitesla is what you get from 10 kiloamps at about a distance of 50 millimeters. So this will tolerate a high current quite close to the sensor. Response time is 2 microseconds. The insertion impedance is very low, less than a picohenry. And the operating temperature, quite broad range, minus 40 to 100 C. It's sealed. It will tolerate water buildup. It'll tolerate ice, and it'll tolerate ice melting. The aperture is 27 millimeters. The weight is very low, 30 grams or an ounce. And the power supply is 3.5 volts to 5.5 volts, less than 85 milliamps. So this can be operated from a USB port or a USB battery. So it's very convenient for in vehicle where it may be used, say, with a battery data logger. We've also developed a larger one, and this might be appropriate for large vehicles, trucks, earth-moving equipment, marine applications. We have two apertures, one a 77 millimeter or 3-inch aperture. It opens very wide so that it can be inserted into quite difficult locations by threading it through. It's also quite narrow in the axial direction, so it doesn't need much space. And then a larger one with a 160 millimeter aperture, or just over 6 inches. And again, it opens very wide, so it can be threaded in, and very narrow in the axial direction. So these are also sealed. And this is probably rather worse than an in-vehicle application with an electrochemical plant. And you can see the current sensors around bus bars. Pretty hard to see them, but the red LED light indicates there's a current sensor there. And these have been operating for many years in this difficult environment. Again, the specifications. This probe comes with several different voltage outputs, and in particular, a 12 milliamps plus or minus 8 milliamps. So that's useful for noisy environments or long cable runs. Current ranges 500 amps to 16 kiloamps. Frequency range DC to 40 kilohertz. The sensitivity error about 1%. And again, relatively insensitive to external magnetic fields. So these can be used adjacent to other current runs with little effect on the output signal. Response time, 10 microseconds. Insertion impedance, again, very low. Minus 40 to 85 C for this one. It's sealed. As I mentioned, two apertures, 77 millimeters, 160 millimeters. Again, quite light, 120 grams for the 77 millimeter, or less than 0.26 pounds. For the 160 millimeters, it's less than 300 grams, or about 0.66 pounds. The voltage range can be from 11 volts to 31 volts and less than 0.8 of a watt. Typically, say, a 12 volt or 24 volt power supply. Now, some test data just to show how these probes can be used. This is a test of the clip with a 60 hertz 250 amps RMS current. And we have a reference transducer. That'll be a green trace in the scope display. And then to increase the effective current, we have 3 turns here. So that's effectively a 750 amps RMS, and this is a 250 amp rating. So the sort of result we get, this green trace is the 350 amps at 60 hertz through the reference. And then this yellow trace is the output from the CPC. And you can see that it very cleanly limits electrically. And there's no overshoot, there's no ripple. It's just a flat limit. And it also limits with the correct sign. So this is a positive going current, and the CPC limits positively. And then as soon as the current within its range again, it follows the current. So if we blow that up, just this region here, so we can look more at the zero crossing behavior, we now have a 1 microsecond, about 0.5 amps. And remember, this is a 250 amp sensor. And you can see the green is the reference, the yellow is the CPC. And you can see that there's essentially no crossover shift. So the phase is maintained, even though the current probe was overloaded by a factor of 3. And there's also no damage. It can be operated continuously in overload, and there's no damage. Now, to show that external fields do not interfere with the probe, this is a 77 millimeter probe. And around the outside, we're putting high currents, about 1,000 amps at each of these positions. And it's a 4,000 amp probe. And the zero offset when these high currents are placed near the outside of the sensor is in each case less than about 0.5%. We can try a similar thing with a steel plate. This is what you might expect if you have one of these current probes in a cabinet. This is a 12-inch 300 millimeter plate, and it's put in each of 4 positions. And as we change these plates around the CPCO, the change in the 300 amp RMS signal is less than 0.1%. Another experiment is to move the primary current conductor around the aperture from being on center to putting it right against the internal surface of the aperture. Again, a 4,000 amp probe, 230 amps RMS. And as we make these changes, including putting the primary current at an angle, then we get a effective current change of less than 1% of the measured current. Now, to indicate stability with thermal cycling, what we've done is start from room temperature, go to -40, up to plus 85, and total cycle about 90 minutes. And we've cycled that for 50 cycles over 70 hours. And we've done this with several examples of both the ClipOn and the clamp-on probe. And the largest changes we've seen are zero offset, about 0.2% of full scale, and the sensitivity about 0.5% of full scale. So now to go into the operating principle of these sensors. They're dependent on Ampere's circuital law. And this states that if you have a current, I, and then you essentially draw any closed line around that current that encloses the current, and you measure B, the vector field of flux density at that point, and a line element, DL, that is along the enclosing line. Then in SI units, you essentially get this. So integrating around a complete loop, B dot DL gives the permeability times the I that's enclosed. Mu zero is the permeability of a vacuum or roughly of air, and I is the current enclosed in amps. And this integral is independent of how the current is located within that closed line, and also the orientation of the current. Often you see this expressed simply where there's a circle drawn around the current element, and the circle is perpendicular to the current, and then the line integral is essentially B times 2 pi r, and that's equal to mu zero I, or you can express it as I equals 2 pi r B over the radius. So in principle, you can measure B at a point to calculate I. The only problem is that if this B has other field contributions from external currents or steel plates or the environment, then you don't get a correct value of I. So what we have done is make a summation approximation of Ampere's circular law. And so we've located sensors that are sensitive to the field along the tangent to the line. So we measure the amplitude B at 0.1, 0.2, 0.3, 0.4, etc. And we make the approximation that the line integral is this summation, a coefficient times the measured field. And these coefficients are determined by some magnetic modeling, and it turns out that we get a result that can be within better than 1% in a wide range of applications. Now, it's important to note that if the current is outside this line, the circular law would say that the line integral is going to be equal to 0 because there's no enclosed current. Similarly, the summation will be approximately 0. So by doing this summation, even though there are external currents and other magnetic fields, we get a very good rejection of the external fields and external currents. Now, because the circular law can apply essentially to any shape, we can use it on a shape like this, which is a U shape that will slip over a bus bar. And this one can be used to measure currents on a bus bar, but it can also be used to measure, say, a cable that's in any position within the U. And this looks something like this. So it's a sort of tuning fork shape. It's very slim in the axial direction, so it can be slipped into a confined space. And again, it's very light. And power consumption is low, so it can actually be used with a battery that's mounted on the outside of this. Current ranges 400 amp to 8 kiloamps, 12 kiloamps. DC to a kilohertz, sensitivity error 1%, response time 2 microseconds. Again, a very low insertion impedance. Operating temperature -40 to 80, 5 degrees C. It's sealed again. The aperture 102 by 30 millimeters, so that's about 4 by 1.2 inches. Mass 65 grams, or about 2 ounces. 3.5 to 5.5 volts, 150 milliamps. So again, this can be used with a USB port. Okay, that's the conclusion of my presentation. It seems that at this stage there are no questions. You can see my email there, ian@gmw.com, our website, gmw.com. My direct telephone number is there. So if you do have any questions later, please come back to me and contact me directly. So my colleague Ben will be giving a presentation on other current transducers that might be used in electric vehicles and electric chargers. And so that will start at about 1:45 Eastern Time, 10:45 Pacific Time. So I hope you join us then. And I see I do have a question. Is there a rule of thumb on the aperture versus the conductor size? And the rule is that as long as the current is within, say, about 80% of the aperture, then it will give a good current measurement. So in this particular case, a current anywhere in this region can be used. Now, that potentially means that this can be used to slip on to live conductors rather than disconnecting the power to use a clamp-on sensor. One can have a battery connected to this and either a fiber optic or a wireless link. And so this could be essentially on some sort of insulating pole and then slipped over a current to take a measure without disconnection, provided that the current can be well within the U. The next question is, are there temperature drift issues? Yes, there is a temperature coefficient for all these probes. And over the full range of operation, say minus 40 to 100, minus 40 to 85, the total drift can approach 1%. Generally, it's smaller than that, but it can be up to 1%. So certainly that has to be taken into account. And as I showed in that slide where we've temperature cycled, even though there are many cycles, the behavior is essentially elastic, so that the temperature change gives a reproducible change in output. So if production measurements or test measurements are made over many different cycles, then they could be reproducible, even though there have been many hundreds of temperature cycles. Thank you. Okay, well, I see no more questions. So again, please contact me directly if you have any questions, and I'd be happy to make contact. Thank you.